faithfully conveying value and interpreting great books from around the world. Hello, this is Sally Book Talks. Today's book we're exploring for you is called The Journey to Discover Extraterrestrial Life. The subtitle is From Goldilocks to Tardigrades. When it comes to alien life, it's a topic that fascinates many sci-fi enthusiasts. In Hollywood sci-fi films like E.T., Star Wars, Avatar, and 2001 Space Odyssey, we see all kinds of imagined alien life forms. So, does extraterrestrial life actually exist? And what might they be like? Actually, there's a specialized branch of astronomy called astrobiology dedicated to studying alien life. Today's book is a popular science work that systematically introduces astrobiology. The author Louisa Preston is a renowned British astrobiologist and professor at Birkbeck, University of London. A researcher for the UK Space Agency's Aurora program, Preston explains astrobiology's framework and latest developments in this book, thoroughly addressing public questions about alien existence, forms, potential locations, and search methods. All right, now we'll explore the book's main content through three key questions. First, what conditions are necessary for life to exist in the universe? Second, what progress has been made in searching for alien life within our solar system? Third, how do scientists explore extraterrestrial life in deep space beyond our solar system? All right, let's begin with the first question. What conditions enable life in the universe? Before answering, the author shares the Grimm's fairy tale of Goldilocks and the Three Bears. Here's the story. A forest cabin housed three bears, Papa, Mama, and Baby. One day, Goldilocks got lost and entered their empty home. Finding three chairs, three porridge bowls, and three beds, the exhausted girl chose the medium-sized chair, ate the medium-temperature porridge, and slept in the medium-firm bed. The author suggests that choosing what's just right reflects Goldilocks' instinct, an instinct shared by all life. To search for extraterrestrial life, we should first look for environments suitable for life. This inspiration came to astronomers from the Goldilocks and the Three Bears fairy tale, leading them to propose the Goldilocks zone for life. The concept of the Goldilocks zone. Goldilocks is the transliteration of the English name. The Goldilocks zone is also called the habitable zone, life zone, or green belt. Life first requires a star to provide stable energy, but the birth and death of stars are common in the universe. So for a star to foster life on its planets, it must first ensure its own safety by positioning itself in the galaxy's Goldilocks zone. Take our solar system. It's in the Milky Way's Goldilocks zone. Our galaxy resembles a spinning straw hat, with the solar system midway along the brim, far from dense star clusters. This offers life a relatively safe, stable, and habitable environment. Because here, there are no violent supernova explosions or matter-devouring black holes. Proxima Centauri, the nearest star, is 4.2 light-years away. Low stellar density eliminates collision risks, making this region a galactic Goldilocks zone. Several such Goldilocks zones exist in the Milky Way, all potentially habitable. For life to emerge on a planet, it must orbit within its star's Goldilocks zone. Simply put, this zone is at just the right distance, not too close or far, not too hot or cold. Planets here receive precisely the right amount of stellar energy. A star's size and temperature determine its specific Goldilocks zone. For our Sun, this zone spans 0.75 to 1.9 astronomical units. 1 astronomical unit is defined as the average Sun-Earth distance. Earth sits perfectly within this solar Goldilocks zone, ideal for life. Yet Earth hosts life not just from being in the Goldilocks zone, but also because it meets three crucial conditions. First, there must be abundant organic matter. Amino acids and other organic compounds are the foundation of life on Earth. Life on Earth began with simple amino acids. Through continuous synthesis and evolution, They produced complex organic substances like proteins and DNA, gradually developing into more complex life forms. Second, there must be ample liquid water. Early life evolution on Earth occurred in water. Water is the most vital substance for life. It forms the basic unit of cells, and organisms rely on it for metabolism. Additionally, Earth's suitable temperatures allow large amounts of water to exist in liquid form, meeting the needs of living beings. Third is a long-term stable environment. Most life can only endure temperature changes of tens of degrees. If too hot, proteins denature. If too cold, liquid water freezes and organisms die from dysfunction. Moreover, life has relatively strict requirements for atmospheric pressure, air composition, oxygen levels, pH in water or soil, salinity, and more. It has been 3.7 billion years since the emergence of the most primitive life on Earth. During this time, Earth's environment experienced many fluctuations and extreme climates, like multiple ice ages. Yet, during ice ages, relatively warm areas near the equator always provided refuge for some life, preventing total extinction. As ice ages ended, Earth regained vitality, ensuring the continuity of life's evolution. However, in the universe, drastic environmental changes are actually quite common. On many planets, temperatures often fluctuate by hundreds of degrees in short periods, posing a major threat to life. For example, on Mercury, daytime temperatures under direct sun can soar above 430 degrees Celsius. At night, heat dissipates rapidly, dropping below minus 170 degrees Celsius. A 600-degree temperature swing makes Mercury like a living hell. Life simply can't endure such torment. Earth's long-term stable environment relies on its atmosphere. Earth's atmosphere has moderate thickness, so during the day, not all solar energy reaches the surface, preventing excessive temperature rises. At night, greenhouse gases like carbon dioxide and methane in the atmosphere protect against excessive temperature drops. Moreover, the atmosphere blocks harmful radiation, causes interstellar debris to burn up from friction when approaching Earth, and minimizes meteorite impacts. For Earth's organisms, only a long-term stable environment allows life to thrive. But this doesn't mean that life absolutely cannot survive in extremely harsh environments. For example, in Earth's extreme environments, like snowy mountains, deep-sea polar regions, and deserts, lives an incredibly resilient species. The book's subtitle is Goldilocks and the Tardigrade. If Goldilocks represents the delicate life common on Earth, then the tardigrade is the exceptionally tough and persistent ninja. The tardigrade's English name is tardigrade. It's chubby, and some describe it as an 8-legged panda. Tardigrades are found worldwide in aquatic environments, but they're hard to spot because they're translucent and less than half a millimeter long. You can only observe them under a microscope. The tardigrade's greatest feature is its extreme survivability. In harsh conditions, they contract into a barrel shape called a tun by scientists, allowing them to survive. Scientists have tested tardigrades with high heat, extreme cold, high pressure, intense radiation, high concentrations of toxic gases, and found they withstand these harsh environments well. Astronomers have even taken tardigrades to space, exposing them to cosmic extremes, and found they survive. Their tuned state is more effective than human spacesuits. This discovery gives astronomers new insights into the search for extraterrestrial life. In searching for extraterrestrial life, humans shouldn't just focus on the Goldilocks zone. They must also consider other areas. Outside the Goldilocks zone, planets with organic matter and water may exist, possibly harboring resilient, lower life forms like tardigrades. All right, that concludes the first part of the book. What conditions are needed for life to exist in the universe? Astronomers believe that life in the universe always emerges and evolves in suitable regions, like Earth in the solar system's Goldilocks zone. Moreover, abundant organic matter, liquid water, and a long-term stable environment are crucial for life's existence and evolution. However, we can't ignore life's resilience. In areas far from the Goldilocks zone, some lower life forms might exist. You may have noticed that when discussing conditions for life in the universe, the author always uses Earth as an example. Indeed, for thousands of years, Earth has been the only planet known to harbor life. But with continuous progress in astronomy and space technology, since the 20th century, humans have ventured beyond Earth and embarked on the journey to explore extraterrestrial life. Now, let's move on to the second question in this book. What progress has been made in searching for alien life within our solar system? There are 8 planets in our solar system. We'll start with Mercury, the closest to the Sun. As mentioned before, Mercury has a harsh environment, unsuitable for life. Mercury's environment is so harsh because it's too close to the Sun. All its water and atmosphere have been evaporated away. Without an atmospheric shield, Mercury has a temperature swing of 600 degrees between day and night. In 1974, NASA's Mariner 10 probe explored Mercury and confirmed this. Mercury is a barren wasteland with no life due to its closeness to the Sun. However, Venus and Mars are Earth's neighbors and the planets most similar to Earth. Both lie near the edge of the Goldilocks zone. So could there be life on Venus or Mars? Let's start with Venus. It's 0.8 times Earth's distance from the Sun and 0.7 times Earth's mass. Logically, its environment should resemble Earth's. Since the early 17th century, when Galileo invented the telescope, astronomers have observed this planet, but could only see its thick, fog-like atmosphere, never clearly viewing the surface. What is Venus's surface like? For a long time, people speculated Venus had a highly advanced civilization, with that fog-like atmosphere being smoke from giant factories built by Venetians. But in 1962, when human probes reached Venus, they were greatly disappointed. Its environment is even more terrifying than Mercury's. Venus's surface temperature consistently stays above 400 degrees Celsius. Even metals like lead melt instantly at such heat, and temperatures don't drop even at night. Here, not only is liquid water impossible, but proteins in living organisms would denature and decompose instantly, so no life can survive. Moreover, Venus's surface is 100,000 times drier than Earth's, with atmospheric pressure 89 times that of Earth. Why is this so? Earlier we mentioned that the atmosphere is Earth's guardian, but for Venus, it's the source of disaster. Venus's atmosphere is extremely thick, and 96% of it is greenhouse gases. In contrast, Earth's atmosphere has only 0.032% carbon dioxide. Venus's atmosphere is like covering the planet with thousands of blankets, trapping almost all the heat inside. Since Venus is unsuitable for life, what about Earth's other neighbor, Mars? Mars is 1.5 times farther from the Sun than Earth, with only 1/7 of Earth's mass. Similar to Venus, when people first pointed telescopes at this red planet, they discovered many stripe-like structures. Some scientists speculated that these might be canals, imagining they were built by highly civilized Martians. However, when the Viking 1 probe landed on Mars in 1976, it was discovered that Martians simply didn't exist. Mars's surface is covered in icy deserts, appearing equally barren, with an average temperature of minus 55 degrees Celsius. The reason Mars is so cold is that its atmosphere is very thin, only 1% of Earth's atmospheric density. However, astronomers speculate that billions of years ago, Mars may have had an atmosphere similar to Earth's, but due to its smaller mass and gravity, it couldn't retain the atmosphere, causing it to gradually thin out. Although Mars is quite cold, it's still the planet in our solar system with the environment closest to Earth's. For this reason, Mars has become a focal point for astronomers, and exploration has never ceased. Especially in the last decade or so, rovers like Spirit, Opportunity, Phoenix, and Curiosity have successively landed on Mars, continuously providing us with firsthand information. We all know that liquid water is a crucial prerequisite for life, and data from Mars rovers indicates that Mars once had abundant liquid water. Although liquid water hasn't been found on Mars's surface, large amounts of water have been detected. Evidence of its past existence includes rovers finding materials like sedimentary rocks, clay, and pebbles in some regions, which can only form in water-rich environments. This proves Mars was once a planet rich in water resources. So where did the water on Mars go? NASA's Phoenix lander dug up ice just centimeters below the Martian surface. Astronomers believe Mars likely still holds vast amounts of water, all beneath the surface as solid ice. They speculate that if all this ice melted, it could form an ocean averaging 30 meters deep across Mars. Some astronomers even suggest that beneath the surface, not only is there ice, but warm underground lakes near the warmer equatorial regions. Most astronomers agree that billions of years ago, Mars was a paradise for life. But as the atmosphere and water vanished, the environment worsened and life gradually faded. So, does life exist on Mars today? Although no direct evidence of life has been found, important clues suggesting its existence have emerged. Um, for example, methane levels in certain areas of Mars's atmosphere spike rapidly, considered a potential sign of biological activity. Though likely only lower life forms like bacteria exist, current Mars rovers continue working, and we may discover actual life there soon. Are astronomers' searches for extraterrestrial life limited to Mercury, Venus, and Mars? Of course not. Astronomers focus on these three because, like Earth, they're metal rich with solid surfaces called terrestrial planets. The solar system's other four, Jupiter, Saturn, Uranus, Neptune, are completely different. They have low metal content, no solid surfaces, and are mainly hydrogen and helium, resembling giant clouds, hence called gas giants or Jovian planets. Jovian planets are far from the sun, beyond the Goldilocks zone, and extremely cold, often minus 100 to minus 200 degrees Celsius. Hydrogen and helium become liquid, and without solid surfaces, conditions are brutal. Astronomers believe these four planets are unsuitable for life. Although these Jovian planets are inhospitable, their moons have sparked significant interest. Previously, astronomers have explored moons of terrestrial planets too, and they have very few moons. Mercury and Venus have no moons. Earth has only one moon, the Moon, and Mars has just two. None have life, but Jovian planets have numerous moons, like Jupiter with 79 and Saturn with 62. These moons are somewhat similar to Earth, with solid surfaces, and astronomers have found signs of possible life on some. For example, Europa, Jupiter's moon, Enceladus, Saturn's moon, and Titan, Saturn's moon. Let's start with Europa. It's not Jupiter's largest moon, but its composition is quite Earth-like. More importantly, Europa has vast amounts of water, but due to its great distance from the sun, Europa's surface is covered by thick ice, estimated to be tens or even hundreds of kilometers thick. Scientists have found many cracks in this ice, and beneath them lies a warm, vast ocean. Although Europa is far from the Goldilocks zone and gets little solar energy, it has rich geothermal resources that can provide energy for life instead. Europa's ocean water is very active, constantly heated, creating those surface cracks, similar to life existing under Earth's polar ice caps. Under Europa's ice cap, seawater stays warm long term, so life might exist there too. Immune similar to Europa is Enceladus. Though only 1/6 Europa's diameter, it also has an ice cap and subsurface ocean. Scientists have also observed plumes occasionally erupting from cracks in Enceladus's ice. This likely means the moon has intense geothermal activity and a warm ocean. Titan's situation differs. It's more like Earth's surface with sand dunes, lakes, oceans, flowing rivers, and similar weather patterns. But astronomers speculate Titan is extremely cold, and its lakes, oceans, and rivers contain not water, but liquid methane and ethane. Thus, it's called the solar system's petrochemical factory. But can methane and ethane replace water as the basis for life? This is a research topic that astronomers are deeply fascinated by. Beyond searching for life on planets and their moons in our solar system, astronomers are also targeting comets. Comets are mainly composed of a mixture of ice and rock. Even though comets freeze when far from the sun and scorch when near it, making them unfit for life, astronomers have found amino acids key to life's origins on Earth on many comets, with a wide variety present. So, some astronomers speculate that Earth's amino acids might have come from comet impacts. Although comets don't host life, they've sown the seeds of life on our planet. All right, that wraps up the second part of the book. While astronomers haven't discovered life beyond Earth in our solar system, they've found clues suggesting it on Mars, Jupiter's moon Europa, and Saturn's moon Enceladus, where simple life forms might exist. Moreover, many astronomers think comets, while lifeless, are rich in amino acids, and Earth's life may have started from those delivered by comet strikes. But it's clear now that any life beyond our solar system would likely be primitive. To find advanced, intelligent beings like humans, we need to search outside the solar system. Next, we'll cover the book's third part, Stepping Beyond Our Solar System, how astronomers search for alien life in deep space, and what advancements they've made. As we discussed earlier, the Goldilocks zone is key for life, and astronomers first look for planets in stars' habitable zones to find alien life outside our solar system, a task known as hunting for exoplanets or super-Earths. But spotting exoplanets isn't easy. They're often small, extremely distant, and don't glow, so observing them is tough. Before the 1990s, some astronomers even thought our solar system was the only one with planets. But in 1995, the first exoplanet was found, named 51 Pegasi b, rapidly orbiting the star 51 Pegasi. So, how do astronomers discover exoplanets? Actually, they observe stars using space telescopes. When a planet transits a star's surface, it causes the star's brightness to drop by 1/10,000, and this usually lasts between 1 to 16 hours. This change in brightness is periodic, and by repeatedly observing this periodic change, we can confirm a planet's existence. Using this method, more and more exoplanets have been discovered. For example, the Kepler Space Telescope found over 2,600 exoplanets during its 9-year service. So, some of these planets happen to be located within the Goldilocks zone. Of course, being in the Goldilocks zone doesn't guarantee advanced life exists, as seen with Venus and Jupiter. Astronomers also evaluate the discovered exoplanets considering their mass, volume, distance from their star, temperature, and other factors. As a result, they've found many super-Earths that are very similar to Earth. For example, one exoplanet called Kepler 452b is very similar to Earth. Kepler 452b is located in the Cygnus constellation, about 1,400 light-years away. Its size and distance from its star are very similar to Earth's. In its star, Kepler 452 is also similar to our Sun. Astronomers speculate that this planet likely has an atmosphere and water suitable for life. Even more excitingly, this planet is about 1.5 billion years older than Earth. This also means there's a chance that life more advanced than humans on Earth could have evolved there. Besides actively searching for Earth-like planets outside our solar system, some astronomers have shifted strategies to focus on receiving signals from advanced alien life. For example, The Search for Extraterrestrial Intelligence program, abbreviated as SETI, was initiated by the University of California, Berkeley. Its goal is to analyze signals captured by telescopes worldwide using computers globally. Any ordinary person can join this program by downloading and running a free application on their computer. In other words, anyone can use their personal computer during free time to help scientists analyze and compute signals from radio telescopes, checking for signals from advanced alien life. However, so far, this search program hasn't discovered any confirmed alien signals. Since humans haven't found alien intelligent life yet, astronomers are split between pessimistic and optimistic views on whether it exists. The pessimists think Earth might be the only island of intelligent life. For instance, the famous Drake equation, proposed by American astronomer Frank Drake in 1960, calculates how many alien civilizations in the Milky Way might communicate with us. Simply put, the Drake equation multiplies 7 variables: the number of stars in the Milky Way, the fraction of stars with planets, the number of Earth-like planets per system, the fraction where life evolves, the fraction where intelligent life develops, the fraction that can communicate, and how long such civilizations last. You don't need to memorize all 7 variables. But here's the thing. If any one variable is 0, the chance of finding alien intelligent life in the Milky Way drops to 0. Some astronomers calculated that there's over a 50% chance humans are the only intelligent life in the Milky Way. And however, more astronomers stay optimistic about finding advanced alien life. Because right now, we've only found a few thousand exoplanets, but the Milky Way alone could have up to 400 billion planets. There are way too many Goldilocks zones out there, meaning endless possibilities. Even without finding advanced aliens yet, some astronomers are starting to classify alien civilizations by level. For example, in 1964, Soviet astronomer Nikolai Kardashev classified alien civilizations by their energy use, called the Kardashev scale. And it divides alien civilizations into 3 types: Type 1, Type 2, and Type 3, where Type 1 can harness all the energy of its home planet. Type 2 can control and use the energy of its host star. Like, Type 3 can harness the energy of an entire galaxy, like the Milky Way. By this scale, humanity's Kardashev rating is 0.7. We can't fully use Earth's energy yet and are still far from even a Type 1 civilization. Building on the Kardashev scale, some astronomers believe that in the universe there even exist alien civilizations capable of controlling the entire cosmos, known as Type 4 and Type 5 civilizations. They can harness the energy of the entire universe and achieve space-time travel to any location in the cosmos. So looking at the entire universe, humanity's stage of development is likely still very primitive. Therefore, some astronomers think that labeling humans as intelligent life is a bit of a stretch. Thus, the author of this book highly endorses the zoo hypothesis, which suggests that humans are like animals in a zoo. Currently, our level of technological advancement is like a cage, firmly restricting us within certain limits, preventing us from discovering other alien intelligent life. Of course, if Type 4 and Type 5 civilizations really exist as predicted by astronomers, they'd likely view humans as too primitive, unable, and unwilling to communicate with us. Just like how we observe bacteria under a microscope. They don't realize humans exist, and we can't communicate with them either. All right, that wraps up the 3rd part of the book, Stepping Beyond the Solar System. Astronomers search for alien life by seeking out super-Earths outside our solar system that resemble Earth. Additionally, astronomers are dedicated to receiving signals from advanced alien life to prove its existence. Regarding the existence of advanced alien life, astronomers are divided into optimistic and pessimistic camps. At this point, we've covered the main content of the journey to discover extraterrestrial life. Faced with the vast universe, humans have long pondered whether we are truly the only lonely existence in the cosmos. Technological advancements have allowed us to continuously expand our horizons, discovering more distant alien worlds. It also makes us realize that despite, constant progress in technology, human power remains insignificant in the vast universe. Discovering extraterrestrial life and unraveling more cosmic mysteries still depend on continuous breakthroughs in human technology. All right, the journey to discover extraterrestrial life. That concludes our interpretation for today. Listening notes are below the audio. For the next great book, we'll see you tomorrow.